Welcome to the 9th lecture in the SATACS category theory course. We are now in 2025, and we have after this one more lecture to go. Last time we talked about universal properties, and we saw that there are some universal properties that can be described in terms of what we call limits and colimits in a category. These are examples of universal properties. I hope you can see my screen, right?
Yes, we do.
But these are only one type of universal. Let me actually list them separately, because although they are dual concepts to each other, when we fix a category, they are, in most cases, very different from each other in that given category. But these are only a couple of special kinds of universal properties, and there are much more. Before going into what I really want us to talk about today, I want to give you a feeling of one or two other examples of universal properties that are kind of similar to limits and colimits, but they are not either limits or colimits. And when I say similar, what I mean is the following. So you can consider universal properties inside a given category. And last time we saw that some of the universal properties are stated in such a way that they are confined within a given category, but some of them are stated in such a way that they are maybe deal with several categories at the same time. And this second kind will be our focus later on today. Limits and colimits, though, they are of the first kind, but there are more universal properties of the first kind that are not covered by limits and colimits. I want to give you an example of that. Inside a category, when you have a limit, as you might recall, you would be given a diagram, and the limit of that diagram is a universal cone over the diagram. So it's an object with a family of morphisms into the objects of the diagram, and it has the universal property that if we have any other such cone, then there will be a unique morphism into my limit, so that all the triangles that need to commute do commute. A colimit is dual to this. So instead of a cone, we have a cocone. And then everything else is similar. The arrows now face the other way. And so the universal property requires the existence of a unique morphism going out of the colimit. And as such, we can view them as kind of tools for constructing things inside a category. So basically, you start with a certain diagram, and then your limit, you can view your limit as a thing you want to construct out of your diagram. Now, there are many examples of these constructions that capture important constructions in mathematics. Of course, the construction of sum and product of objects is an example, as we already know. So we can say that universal properties inside a category can be viewed as methods of construction. So an example of that is sum of objects Another example is product of objects. Quotienting an object by an equivalence relation or a congruence for other structures other than sets, especially algebraic ones, is also an example of a co-limit, and we had a little glimpse of that last time. So quotient is also captured here, and there are many other constructions that are examples of limits and co-limits. So all of these are examples of either limits or co-limits. Let me first say co-limits because I put some first. Co-limits or limits. Of course, the initial object and the terminal object is also there, as we know, because they are co-limit and limit respectively over empty diagram. We already know that, right? So we know how to view initial object as empty sum. But there are other constructions inside a category that are not captured by limits and co-limits, and one of the most important ones is the one that I want to talk about now. It's called a sub-object classifier. A sub-object classifier is also defined by a universal property. So what is a sub-object classifier? In the category of sets, okay, let me first say here that this is which is neither a limit nor a colimit. So it will turn out that this is an important construction in a category that will allow you to, if you have this, you don't always have it, and if you have it, this will allow you to do almost all of mathematics. I mean, you need a bit more than just that. You also need limits of finite diagrams, and I think maybe all, or maybe you also need a little bit more. I'll confirm a bit later. But if you have that construction, it will allow you to do all of mathematics inside your category. So your category will be almost as well behaved as the category of sets, so that you can interpret models of logical theories inside your categories, and you can define things the way you define in sets. So it's a very powerful construction, and hence it's worth talking about. But I'm going to motivate this concept, this specific universal property, from the category of sets. So something very intriguing happens in the category of sets, namely that if you take a set X, right, and you take its subset, so let's take a subset of a set X. I'm drawing this hooked arrow to represent that this map from S to X is a subset inclusion. Everything gets mapped to itself in the other set. So an element S here would be mapped to itself. Now, forming a piece of your structure is a very important construction. I mean, it's so important that nobody talks about it, but it's there, right? For instance, the torus that we were talking about last time, the donut-shaped geometric object, we can view this as a piece of the three-dimensional space. So we're kind of isolating something in your structure, right? And that's what we're doing here. And in a general category, we can capture this idea using the notion of a monomorphism. So let me briefly define what it means here. What is a monomorphism? A monomorphism is a morphism M from, let's say, A to B, such that I'm going to give an unconventional definition, but a well-known defining property using limits. So it's a morphism such that the following is a limit. So we will consider a diagram with M and another M. So two M's placed in such a way that the domains are drawn separately, but their codomain is not drawn separately. It's the same node of the diagram. And this is going to be our diagram. Okay. And now its limit would be, I mean, a certain kind of a cone, right? But I'm going to force this cone to be of specific kind, and namely, I'm going to force this cone to be of the form with 1A here, M here, and 1A here. So the identity on the two sides, and in the middle, the M. Now let's understand what it means for this diagram to be a limit. So that means that for any other cone, there is a unique map, right? So if I have a cone, what it does mean to have a cone over this diagram? Well, it means to have three maps, right? Three morphisms, 1, 2, and 3. So this is our cone, but not arbitrary, such that some triangles commute. Namely, this will have to commute, and this will have to commute. So let's label these A1, B, and A2. So for any such data, A1, B, and A2, so for any A1, B, and A2, such that the triangles commute, so such that MA1 equals B and MA2 equals B as well. And of course, because they're both equal to B, from the point of view of just basic logic, I could have just said that they're equal to each other, and then B is uniquely determined. So I actually don't really need B. B will be recoverable from A1 and A2, right? So what matters here is A1 and A2. Now I need to say that there exists a unique morphism, right? So I need to say that there exists this unique morphism from C to A.
So what we just wrote about A1, B, and A2, it's just saying that this cone is permissible.
Yes,
Okay.
it says that this thing is a cone. The yellow thing is a cone.
Yeah, yellow one. Okay, fine.
Yeah. So now I need to say that there exists a unique blue arrow from C to A. But observe that this will be unique by the property that composed with identity, it must be A1, and composed with M, it must be B, and composed with identity, it must be A2, right? So the three triangles here are this, this, and that. But now, if we're a bit clever about this, something composed with identity will be equal to that thing, right? So we're basically saying, with this triangle, we're basically saying that this morphism must be equal to A1, right? And it will always be unique because, I mean, if it exists, it will be unique because, once again, if I force this blue arrow composed with a white arrow to equal A1, then I'm forcing that blue arrow to be A1. So, of course, it's unique. Does that make sense, Okwatisa?
Yes, completely.
So we don't have to care about uniqueness. It will come for free by the nature of our proposal for a cone here, for a limiting cone. But its existence is arguable. So when would it exist? Well, it would exist whenever I can fit in A1 here, because that blue arrow will have to equal A1, but also I can fit in A2, but now they have to be equal to each other, therefore. But now furthermore, they composed with M must be B, but we already know that's true. So the only requirement we're actually asking for is that we have that A1 equals A2. So the definition of a limit in this case simplifies to saying that for any A1 and for any A2, such that M of A1 and M of A2 are equal to each other, we can really forget about B. Saying that we have a B so that both of them are equal to that is the same as saying that they're equal to each other. So whenever A1 and MA2 are equal to each other, A1 equals A2. So I can now write this as an implication. MA1 equals MA2 implies A1 equals A2.
Sorry, Zero, could you like show once again which diagram forces A1 and A2 to be equal?
Yes. So going back to this diagram,
Yeah.
we're saying that there is this unique blue arrow. Now, because this triangle needs to commute, the blue arrow must be A1. And because this triangle needs to commute, the blue arrow must be A2.
So, okay, fine.
Yeah. And so they have to equal when the blue arrow exists, but if they equal, blue arrow does exist because we can just take the blue arrow to be them. So it's both ways. And then ensuring that the middle triangle commutes is something we already know about A1 and A2. So we don't have to bother about that. So eventually we get this condition that whenever MA1 equals MA2, then A1 must equal A2. And this is something we've seen before, right? This looks very familiar, right? Can you maybe tell me what it looks like, this thing?
Well, injectivity.
That's right. It looks very much like injectivity. It would be exactly injectivity if I put brackets around here, right? But then I can really think of elements of my set A as morphisms because I could take C to be a singleton set. If C were a singleton set in the category of sets, right? Sorry, I think you wanted to say something, Gokotisa.
No, I had the same that is an injective map. It's fine.
That's right, yeah. So if C were a singleton, I mean, this property has to hold for every C, right? In particular, when we are in the category of sets, it will hold when C is a singleton set, a one-element set. And then naming morphisms A1 and A2 will be equivalent to naming elements. And so this property will force M to be injective. But it actually tries to force more, right? Because we now have this implication not just for the case when C is a singleton set, but for any object C. But it turns out that once a map is injective, it will satisfy this even for any C. And it's not difficult to see that because the first equality, if these are, so in the category of sets, the first equality becomes that MA1 of C equals MA2 of C for every C in C, right? That's what it means for two functions to equal. And when M is injective, for each individual C, this will imply that A1C equals A2C. So we will get that A1C equals A2C for every C again. So in other words, for the category of sets, these monomorphisms will be exactly the injective functions. And in general, in other categories, especially in the algebraic ones, monomorphisms give us the right notion of embedding of one structure in another. So for the category of groups, they will turn out to be exactly injective group homomorphisms. For the category of rings, the same. And for all sorts of algebraic categories, it's always like that. For geometric ones, they're not quite the right notion of embedding. For instance, subspace inclusion of topological spaces will not be quite this. Injectivity does not, so being monomorphism does not guarantee that you don't have some extra open sets in A that are not inherited from B. And when you have a subspace of a topological space, you want your structure on A to be completely inherited from B. So you need a special kind of monomorphism, not just any monomorphism. Anyway, so I had to make this detour, which also is another, also view it as another example of universal property, which in this case is a limit, right? So this was a limit, but now I needed this now to talk about this hooked arrow in a general category, because if I'm going to say something about the category of sets, but later I'm going to abstract it to a general category. So now we know that what I will mean by a hooked arrow in a general category will simply be a monomorphism, something that is a monomorphism. So M, that's a map from a monomorphism from S to X. So in other words, a map such that a diagram similar to this is a limit. Or equivalently, that this implication holds for arbitrary A1 and A2. Okay, so now let's go back to the category of sets, where we have a special kind of monomorphism in this case. It's an embedding, and in category theory we don't care about the fact that every S is mapped exactly to itself, because some information is lost. I mean, things are only the same in category theory up to bijections, up to isomorphisms, and I could have another injective map that doesn't have the same elements as X, but there is a nice bijection between them, between that S and S prime, so that the triangles commute, and that would have been just as good. But since we are in the category of sets where we have this luxury of considering these actual embeddings, let's consider one. And what I was going to say here is that there is this very fascinating phenomenon that happens in the category of sets, namely that you can describe this piece of your structure, you can also describe it as a quotient of your structure. So in general, substructure and quotient structure are very different things, right? Just to give you a pictorial example of this. So when I have some structure, some mathematical structure that say consists of elements, what is a substructure? Well, a substructure is usually its piece that's closed under whatever operations we have there, if it's an algebraic one, right? What is a quotient structure? A quotient structure is when we decide to stick together some of the elements to disregard their differences. And so we squash these things together. And in this specific case, we will get a structure consisting of 5 elements, right? So as a map, it goes completely opposite way, all right? As a map, this one goes this way, and the other one goes out. The other one goes in, and the other one goes out. Now, in the category of groups, for example, you can have the group of integers. You can have the group of integers modulo 2. And you can view this, or maybe let's use 12 because this gives us clock. You can view this as a quotient structure of integers. So every number gives you a number from, let's say, 0 to 11 or 1 to 12. Since it's a clock, let's think of it as 1 to 12. It gives you a number there. And this is actually a very useful map because this is how we keep track of time. It's a quite clever thing that people have come up with to have a finite set describing time, so that to kind of avoid the problem of the fact that there are infinitely many numbers, the time is infinite. Now, this map has a kernel. All the numbers that are seen as the number 12. So there will be multiples of 12, right? It will be 12z. And in a subject called homological algebra, which is a very fascinating subject, this gives us an exact sequence. It's a completely different story, but exact sequences also, by the way, defined using universal properties.
So
are
maybe
very
a question
important.
about this exact sequence stuff.
Yes.
So if I remember it correctly, if we have, for example, a short exact sequence of abelian groups and it splits, it's a right split or equivalently it splits from left, then we have that phenomena that in the middle you have this summand of the quotient and the substructure. Are you talking about something like this, or
Yeah. So
because
if this
like
was
in this
indeed
case,
split,
yeah,
if it was possible to go back, it's not possible, and that's why I gave this example. But if it was possible, then we could represent Z as Cartesian
summand.
product of, or sum, because for abelian groups, sum and product turn out to match with each other. So we can represent it as product or sum of these two. And that would be a special kind of short exact sequence. It's called a split short exact sequence when we have a way to go back.
So in this case, we have that sub-object is quotient as well. So is that what you mean? Oh.
No, it's not. These are very different things. So these are the numbers. This is an
No,
infinite set.
not in this case, not in this case, because it's not
Yeah,
split sequence.
exactly. In the split case, you're right. Yeah, in the split case, this will end up being both a quotient and a sub-object, because this thing will be a monomorphism if it was split, but it's not. So we have this monomorphism from this object to that object. So that describes as a substructure for us. So in this case, as I said, it's all the numbers that are multiples of 12. So n times 12, where n is an integer. And this is, of course, just the numbers from 1 to 12 as a set. And you can see that having a piece of Z as a group, it must be a subgroup, is very different to having a quotient group, because Z12, we will never be able to think of it as a subgroup of Z. The reason for that is because Z12 has this special element that when we add this element to itself enough number of times, we get back to that element, right? And nothing like this can ever happen for any element here, unless that element is 0, of course. But if I map my 1 to 0, then everything will be mapped to 0, and it won't be an injective map anymore. So in general, quotient and a piece are very different from each other. I mean, in a sense, you can really think of a piece being one equivalence class of a quotient. Somehow you can think of it like that, right? But the quotient does much more things than that. And yet, in the category of sets, every time I have a piece of X, a subset of X, I can form a quotient of X that I can then use to recover back my subset. And this quotient of X, and by the way, it will not always be just quotient, it just will be a map going from X to a two-element set. So what is this map going to the two-element set? I want to build it out of M.
So it has to tell us whether an element is the right one or not. So it will be like some Boolean function now.
Yes. So I can think of my two-element set as set consisting of 0 and 1, or I can think of it as a set consisting of false and true. So let me use notation logicians use for false and true. False and true. And when I have a subset of my set, I can view that as one equivalence class. So all the elements in the subset are mapped to true because they belong to the subset, whereas everything else maps to false. So this is how I get this function here out of M. So I can write this down properly. Which of you remembers whether this is a phi or a psi? I think it's a psi. Do you agree with me?
I think so.
Great. So psi m of x equals truth when x is an element of S, and equals false when x is not an element of S. Now this is a very useful function because if you remember back how we count how many subsets a set has. A set has, if a set has n many elements, it will have 2 to the power n many subsets, right? But where does that formula come from? Well, to prove that this is the case, the easiest proof that I know is to take your subset and represent it as such a function. And then you'll be counting how many functions you have from an n-element set to a 2-element set. And always this will be powering the numbers. We already encountered that principle when we were looking into sum and product, that the number of functions from one set to another is the number of elements in the other set to the power of the number of elements in the domain. So it's a useful function, and actually there is a bijection between such things and subsets of X, which is what because of this bijection we can say that the numbers match, right? But this bijection is not just any kind of bijection. This bijection comes out from a universal property.
Is phi a characteristic function in some way of isomorphism in this case?
Yeah, I think that's how it will be called, yes. So this bijection also comes from universal property, and specifically, we can recover M out of this psi M. We can recover it by requiring that something is a limit. And namely, it will be a limit of a similar kind as what we saw here, but the difference is that the M's will no longer be the same. So to do that recovery, we first have to form a diagram over which S will be a limit, and the diagram will consist of the terminal object here. So this is the terminal object, which is in the category of sets, it's a singleton set, a set with only one element, and a morphism that picks out truth. So if this has only one element, in fact, let me think of that element as the truth itself. And so this is then just another hooked map. So it maps T to T, maps truth to truth. Okay, so I've now formed a diagram. This is the diagram I want to consider. And now I want to claim that S will be a limit over that diagram, but there are some morphisms missing, right? a limit must be a cone, and so it needs to have morphism not just to X, but also to this object and to that object. So let's draw them in. Well, the thing is that there is always unique morphism to the terminal object because of the terminal object definition, right? So we don't have to worry about that. We do have such a morphism, in fact, exactly one. And then, just as before, since we want, oh, sorry about that. Since we want the triangles with a middle morphism to commute, we can actually disregard the middle morphism, because just as before, if insertion of middle morphism and saying that this thing is a cone amounts to, let's call this something. Let's call this n. No, let's call this. We will not need it later, so use a letter that we're going to discard afterwards. Let's call it U. U for useless. Actually, it is not useless. It will play its role now. So saying that U equals psi m composed with m, and at the same time, U must equal the other composite, right? We can call this exclamation mark subscript s. And because this is, we should also call this something we call this small t for truth. It picks out the truth element inside this two-element set. And so we then have that U must equal to t composed with exclamation mark s. But of course, these two equalities just amount to saying that, so to say that there exists such a U that has these properties, existence of U with these properties, is to say that those two sides of the equality are equal to each other. So it's equivalent to saying that psi m composed with m equals t composed with this. This is similar to how before we could disregard the this b here, having a b such that we had this equality became similar, equivalent to just having that. So actually, we will have indeed a cone. My S will be a cone, but I just have to make sure that this equality holds, right? And then I will have a cone because this one is unique, and because that equality holds, I can define U to be either side of the equality, and then these will hold as well. So let's now unpack. What does that equality say? That equality says, let's chase my element around the diagram, because it says that this composite must equal that composite, right? So if I take an element S in my top left corner, then it will be mapped to T by this unique map, because there is only one element in the terminal object. And then down here, T maps to T, right? On the left side, though, S maps to S, right? And the question now is whether this maps there or not. But that's how we define psi m, right? Everything that was inside the subset, we were mapping it to T. So it does work. So this commutes. Okay. So what do we have? We have that our S is actually a limit of this diagram. And now the definition of a subobject classifier states the following. I just want to win some space here. Let me copy this picture. Any questions so far, by the way, before I abstract this?
No, I think everything is fine.
Great.
So what does this equality say again?
With this equality symbol here, I'm just saying that chasing this diagram on this side gives me the same result as this side. So I'm just saying that this composite equals that composite.
Fine.
Okay. So now not just that thing will be a limit, which we saw it is, but a bit more will hold, and that whatever more is, I'm going to state it in the definition of subobject classifier. So a subobject classifier, and usually it's not called 2, usually it's called omega. Omega. Well, subobject classifier is an object in a category, is an object omega in a category, such that well, actually, it's not just one object, it's a pair. It's an object together with this. I also need to specify this T-map. Just like a product is not just an object of the product object, it comes together with product projections, and the sum comes together with the product sum inclusion. So also here, this one comes with a certain morphism. Is an object omega together with equipped with a map, equipped with a morphism, equipped with a morphism T from the terminal object to omega. So I need to have terminal object in my category. And in fact, I want to have not just a terminal object, I want to have all possible finite limits. So this concept exists in a category where I can construct limits of things. Maybe I'll add that, but one can also drop that requirement, but then one will have to incorporate some of those limits as part of the definition. So it's an object in a category having limits over all finite diagrams I'm going to put this in brackets, right? So we're only considering a category where such limits exist, and then the terminal object will exist because terminal object is limit over empty diagram, so we don't have to worry about its existence anymore. So it's equipped with a morphism, and then the property is that for any monomorphism M from S to X, so S and X are random objects, there exists again some sort of universal property here. We're saying that something for anything of one kind, some unique thing exists. There exists unique morphism psi M from X to omega, such that the cone I'm going to draw is a limit, such that this S together with all the ingredients we've seen thus far. So this is the unique morphism here. This is my M. This is psi M. This is the thing that omega comes equipped with. And this is a fill-in, which will exist once those composites are equal. So its equivalent existence is equivalent to that, such that there is a limit of the form of this form. So so the top part is the cone over the diagram. By the way, it has a name. It's called a pullback. Limits of this form, when I have two morphisms like this, and I'm considering a limit over that as a diagram, I can always disregard the middle morphism because that amounts to just saying that the diagram commutes. And then I can what one usually draws is in a diamond or square shape, and then it's called a pullback of this. The entire thing is called, I mean, this part is called a pullback of this special kind of element. We encountered that already for describing monomorphisms. They were described as in terms of these pullbacks, and here's another one. So you see, the definition is long, and let me try to fit it in one slide by copying it and making it a bit smaller. The definition is long, and it's sort of higher kind of higher order exactness. Sorry, higher order universal property, right? Because if you look carefully, what we're saying here still doesn't fit. If you look carefully, what we're saying here, we're saying that for every S that exists unique this, right? So when we say something like that, for every something that exists unique morphism, that's sort of a universal property, right? But now the condition we put on this thing, which usually in a usual universal property, the condition we put is that that thing must make some diagram commutative. Here, not only it must make some diagram commutative, it actually must make some diagram itself to be a limit. So in that sense, it's a second order universal property, right? For everything, every this that exists unique that, such that we've got this diagram, and for every cone that exists unique this. So it appears this for every that exists unique, it will appear twice, this combination. And in that sense, it's a second order universal property.
Sorry, can you repeat why it's like higher complexity?
Sorry?
So can you repeat why it's a higher abstraction, or the I'm not sure what word you used here.
So higher order. So a universal property is typically stated like this: for every something that exists unique something, right? In this case, we will be saying for every m that exists unique phi, such that this thing is a limit, right? But now this thing being a limit itself is a universal property. So in this case, the format will be this iterated twice. Does that make sense?
Yeah, it does. Thanks.
Yeah. Now, most universal properties are of this kind, are of first order. There are some of them, and usually they're very important when they come up. There's some of them that are of this kind. And I don't think I have ever seen, unless I'm now misremembering, I don't think I've ever seen a universal property that's of third order. So maybe that's something that will come up in the future of mathematics. Anyway, by the way, together with my former PhD student, Pierre-Alain Jacquemin, who is now working in the Royal University of Belgium, we tried to develop a general theory of universal properties, of the ones that kind of let me say of properties that are expressible in terms of limits and colimits, and this one would be one of them, because on the second step we have a limit. These properties are usually called exactness properties, and in our work we were defining what it means to be first order and what it means to be second order. The terminology actually comes from my father, at least, but interestingly, nobody has actually looked at these things rigorously. So we kind of started pioneering having a unified, as much as possible, theory of these universal properties. Anyhow, why is this second order universal property, why is it true for our case? Let's prove that this thing, we now know that for every m, I can actually find phi m, and we kind of know it's unique, right? Because, well, we don't know it's unique because we haven't looked at the property by which it's unique yet, but the construction we have for this psi m is such that it's uniquely determined by m, right? Map everything in the image of m to truth and map everything else to false. So that's a unique construction, right? But now it will turn out that's the only thing you can do if you want this to be a pullback or a limit. And moreover, it is actually a limit. So we're going to prove that now, that this thing in our previous case is indeed a limit, which will then, by noting that psi m is unique with that property, will prove that number 2, the two-element set, is a subobject classifier in the category of sets. So let's look at that now. Why is this a limit? Why is this a limit in the category of sets? So let me redraw this. So I've got some set X. I've got the two-element set. I've got the one-element set. And I've got this map that picks out the truth value in the two-element set. And I've got this psi m. And I've got S. And this is my cone. So I'm going to do this dashed arrow because we know it can be defined in a unique way, since it will have to be equal to this composite. And we already checked that that part is fine, right? We checked that we do have this map U in our case. Where did we check that? This is where we checked. It was equivalent to this equality, which was verified here. And now proving that this thing is a limit. So this is our diagram, right? Proving this thing is a limit, we need to prove that for any other similar diagram with some set C and functions. Okay, first of all, this one is M, and this is exclamation mark. And functions, let's say F, and let's call them F and G. F and, well, this one will actually be exclamation mark C because there's only one element in the terminal object, right? For any two such things with the middle one, and but once again here the existence of the middle one will just amount to some equality. So for any F such that psi m composed with F equals to this middle thing, which in turn must equal to this. So we can just write it equals to T composed with this exclamation mark C. So when this happens, so for any F, when this happens, it must imply that there exists a unique thing here. Let's call it V. So it must imply existence of a unique V such that what? Such that first of all, M composed with V equals F, right? That's this triangle. Because this triangle commutes, I can compose it with psi n, and we'll get for free that this triangle also commutes. That's the part we can skip. And then we also want this triangle to commute. But that triangle always commutes for free because both this composite and that morphism, they're both morphisms into the terminal object, right? So we just have to write this. Of course, M here is a monomorphism, and we know that the monomorphism has the property that MA1 composed with MA2 implies A1 composed equals A2. So this property here will definitely prove that V's at most one. We cannot have two different V's, because if we had two different V's, we would have MV1 equaling F equaling MV2, and by the monomorphism property, V1 will equal V2, right? So we kind of already know from our previous knowledge that if V exists, it will be unique. So we just have to prove it exists. Now you tell me, if I have a subset inclusion here, and I have a function f here, what does it mean for there to exist a V such that this holds? So if this is nothing other than subset inclusion, to require that there exists V such that this triangle is commutative, what does that mean? What does that say about f? There is a simpler way of expressing this.
It's like a function defined on part of S.
Mm-hmm.
Yeah, I'm a bit confused with the purple brackets, the purple square brackets.
Mm-hmm.
I don't know what they mean. Why are they? Oh, is MV equal F the thing we're operating is what is it? The thing which V is operating on.
So we want to say that if I rewind it a little bit, we want to say that this thing is a limit, right? So if I have a cone, the yellow diagram, there must exist a unique way of connecting the two cones. That's V, right? And then the definition of a limit requires that this V is such that V composed with this must be F, V composed with this must be that, and V composed with that must be that. Do you agree with that?
Mm-hmm.
And so here we've just written this part that V composed with M must be F, because the other will come for free. That's what
Okay,
we're
yeah,
written
yeah.
here. But now we want to simplify this further. So what does it mean for in our case, where we are actually working in the category of sets, and this actually is a subset inclusion? What does it mean for MV to equal F?
That S is the same as C.
Does it have to be the same?
Up to isomorphism.
Well, can't we have C to be empty set, for instance? If C is empty set, this is the empty function. I can have another empty function there. S could have been X, and I will still have this equality, right?
Mm-hmm.
So my function f maps these things into X, and X contains S as a subset, right? And so in order for this function to factorize through this subset inclusion, I will have to have every element C mapping somewhere here, some V of C, which then maps down, but the M doesn't change things, right? M keeps them the same. So it will map down to VC again, but then that will have to match with where C is mapped to by F, right? So F of C will have to equal to VC. So V will be defined the same way as F. That's what it says, right? So let me go back to my question. I try to give you a hint here.
So is it like that, say some sense subset of S itself, and F is actually M but on a smaller part of C?
That's right. So C doesn't have to be subset of S because F doesn't have to be injective. But you're right. So F does something to elements from C. It might be squashing them as well. It doesn't have to be mapping them injectively, right? But whatever F does to C, it must map everything inside S. If at least one element falls out of S, I will never be able to recover that value by first going to S and then composing that with the inclusion, because the inclusion will miss everything outside the subset, right? Does that make sense to you, Kotisa?
So F is a kind of what is it? Equivalence relation in some way.
Not sure about that. The image of F is contained in S.
Okay. Yeah, I don't know. Like it's partitioning, what is it? Elements of S so that we have a space. So that whichever ones we use F on, they will be, yeah, I can't, what is it, complete that thought in my head, but you can continue though.
Anyway, let's see why this works out. So initially I had F such that psi m composed with F equals the other composite, right? And what does that mean for every element of C? If I take an element of C, what is F of C composed with psi m? And it must be equal, according to this, it must be equal to T, right? So once again, we've got here a diagram, and we're now considering an arbitrary cone over it. The yellow thing is a cone over that diagram. And for it to be a cone, it means that this equality holds. So it means this. Psi m composed with F applied to every C will always equal truth. But of course, that does mean that the image of F, the elements on which psi m is true, is exactly the elements of S, right? So that is equivalent. So to say this for every C, that is equivalent to saying that image of F is contained in S, right? And saying that the image of F is contained in S is equivalent to saying that there exists unique V such that MV equals F. I feel like this is not yet clear. That's because we're dealing with a second order universal property. It's twice more complicated than the first order universal property would be.
So the very first question, no, not question, the very first expression equality says just that the elements that lie in image lie in our subset.
Yeah,
Fine.
that's what we said here, and that's equivalent to what you to this, which is what you said, right?
Okay, fine. Because images no, never mind. Yeah, it's clear.
Okay, so once again, what are we saying? So we have this yellow cone. We have this yellow cone over this white diagram. Okay. Now we're unpacking what it means to have a yellow cone over the white diagram. Well, it means to have this triangle commutative and that triangle commutative. That is the same as just saying that this equality holds. Why? Because if this composite equals that, and also the other composite equals that, it just means that the first composite equals the second composite. And if that is true, then we can always pick the middle map to be that composite. So, do we agree on this part of what is so that having this cone, the yellow cone over the white diagram, is just equivalent to having this equality? Do we agree with that?
Yeah, that's fine. Yeah.
Okay. Now,
sorry, when we write that image of F lies in S, does it mean that we identify S with a subset in X, or?
S is a subset of X. Yeah.
Yeah,
S
okay.
is our, we were working in the category of sets, and S is a subset of X that we
So that's something we know. Okay, fine.
Yeah. So we now agree that having a cone is equivalent to having this. Now, what I want to agree with you, Kotisa, is that having this is equivalent to writing this down. Okay. So this is equality of functions. Two functions are equal when their values are equal, right? And here is one value of the left-hand side function. The right-hand side function, because it goes into the terminal object, its value will always be, well, the exclamation mark goes there, but then with composing with t, its value will always be truth, right? So this is a constant value. So we agree on this, on the part that this is equivalent to having this, right?
Yeah, that's fine as well.
Now let's unpack what this means. This is our characteristic function, right? When does it map an element to truth value?
Oh, when that element belongs to the
Subset.
Yeah, to the subset.
But these FCs are all possible values of F, right? So all of them must belong to the subset.
Yeah, okay, yes.
So but all of them is called the image of F, right?
Yeah.
So this is equivalent to this. We are fine so far.
Yeah, that's yes.
Now, if I have my image of F contained in my subset, won't I be able to decompose my function by first going into the subset and then composing with the subset inclusion?
Okay, yeah. So the image is in the, okay, yes, that's true.
Yeah. So the implications we care about are actually this direction. We don't really care about the reverse. It's also true, but we don't need that.
Okay.
So eventually, what do we get? Eventually, we get that if I have a cone over the white diagram, such unique v will exist. That's proving that this thing is a limit. That's what we want to prove. We wanted to prove that that thing is a limit, because that's what the definition of subject classifier requires, that that thing must be a limit. You see here, we were requiring that this must be a limit.
Yeah, so
Any questions?
we don't have to separate it out in terms of proving existence and uniqueness separately. Somehow
the uniqueness, we would have to, we made a bit shortcut. We would have to prove, I mean, we so far proved existence of V, but the thing is that once V exists, it will be unique, because imagine if I had another V prime, already the fact that MV must equal MV prime, already this fact, not to worry about any other properties of V prime, already this will force V to be equal to V prime, because M is a monomorphism.
Yeah, okay.
Yeah. So we showed the second layer of the universal property. We showed this, but now we still want to show that for each M, such psi M itself is unique, such that this thing is a limit. And we're not going to do that, but that's not difficult to show. So kind of, I mean, that kind of comes from, I think it actually comes from the equivalences here. So now will be reversing, right? So if this, let's say for an m, we do have psi m that does make this a limit. It will have to force psi m to be the characteristic function. And one way you can prove that is just to see what it forces. So you could, for instance, okay, let's actually prove that. Let's see how we can prove that, because now it doesn't come to my mind, which means that maybe the proof is not so trivial. So we're dealing with just to remind you again, we're dealing here with a second order universal property, where we want for every m to prove there exists unique phi m such that this thing is a limit. So far, in the category of sets, what we managed to do, in the case when m is a subset inclusion, but the same technique can be adapted to any injective function, we build this psi m, it's the characteristic function of that subset, such that this thing is a limit. But now we want to show that this psi m is unique, that we cannot have any other function that has the same property. So let's suppose we have another candidate. So some other, let's call it phi m. Maybe this is too notationally too similar to the other one. It might confuse us. Let's call it alpha m. That goes to omega. That goes, in our case, it's 2. And here is 1. And this is the truth value map. So let's say we've got another limit of this kind. Again, I can just do the dashed arrow in the middle there. So assume this is a limit. I want to prove now that alpha m must be equal to psi m. We want to prove that alpha m equals psi m. So that will be showing the uniqueness part in this second layer of the universal property, right? So psi m is the one that exists, and now I want to prove it's unique. So when I say this is a limit, of course, I mean that the diagram is the blue one here, and the cone over it is a limit. Let's first unpack what it means for this diagram to be commutative. An element at the top here, S, on the left side will map to S. Then it will map to some alpha m of S, right? On the right side, on the other hand, it will map to the unique element here, which is T, and then that will map to that thing as well. So we see that alpha m of S will have value equal to truth, right? Because here truth is mapped to truth by this T map. Remember, T is fixed. So this will actually equal psi m of S for every S in S. So it's almost what we want, right? We now know that alpha m will have the same values as psi m did on the subset S. We know that. We now need to make sure that the same is true outside that subset, so that if something does not belong to S, that alpha m's value there will be false rather than truth. So it remains to prove that alpha m of x equals false when x is not an element of S. So let's I guess, try to prove this by contradiction. What happens if it wasn't the case? Well, before we move to that, do we agree that this is what remains to be proved?
Yeah, that's
Yeah.
it.
So assume that we actually don't even need contradiction here. I'm going to prove that alpha m, if alpha m of x equals true, I'm going to prove that we will prove that x must be element of S. Okay? And this is how I'm going to do that. I'm going to copy this diagram again. And with that assumption, I'm going to put here the terminal object. And I'm going to build this map here that picks out the element X. Then I'm going to turn this into a yellow cone. So this will become a yellow cone actually. So here I will take identity map. So it's the identity map of the terminal object. And I now need to know that I can insert something here, but that amounts to saying that alpha m composed with X equals the same thing as what this composite gives us, which is always constantly true, right? It must equal to T. But that is indeed equivalent to saying that this is true, right? Because what is the unique value of X here? So it's X, so one has only one element, T. So we're saying this must equal to T of truth. But X of T is my element X. I'm representing an element as a map. So maybe if I want to be more precise, I should use a different notation here. If I use underline here, then X underline of T is the element X. And so that equals T to truth. And that was exactly our initial assumption. So in fact, our assumption guarantees that we have, and it actually exactly says that we have this yellow cone over the blue diagram that is given by representation of the element X as a morphism here. But then by the fact that the white diagram is a limit, there must exist something here, right? A unique thing exists here, yeah? Unique V. And as we said before, existence of this V, so it exists such that MV will equal X. But we already kind of understood this before, that is the same as saying that the image of X underline, that should be X underline, yeah, is contained in S, right? But what is the image of X underline? It's just a single element, right? It's element X, so X is contained in S. Does this make sense?
Yes.
So we kind of see how very precisely the fact that this is a limit captures the idea that alpha m must be the characteristic function of M. And then the proof is complete. So we've now proved that not only for every M, only for every M there exists such psi M, making this a limit. Moreover, for each M, such psi M is unique, that makes this a limit inside the category of sets. So we've ended up going today in a slightly different direction than what I initially promised Alexander we would do. But I don't regret that because it was nice to be able to touch on this very important topic. So we are now ready to formulate a definition of a very important class of categories. And I'm just looking up the definition on the internet because I hardly ever work with this class of categories, just to make sure that I've got all the axioms right. So where are we now? Let me zoom out. Okay, that's where we are. An elementary topos is a category in which limits of all finite diagrams exist. This is something we already required for formulating the definition of a subobject classifier. A subobject classifier exists. It will actually traditionally is a third condition. A subobject classifier exists. And exponentiation exists. In other words, the category is Cartesian closed, and we're going to discuss what that means in a moment. For the category, it's another universal property. The category is Cartesian closed. It will be some very nice behavior of products. Now, this is something that is defined by universal property. It's the limit we talked about in the previous lecture. This is something we talked about today. And let's briefly talk about this without any proofs, just to tell you what the definition is. And then I'm going to tell you why these three axioms together are extremely powerful. And in fact, they can be simplified further. These two can be put together by saying that so-called power objects exist. So you kind of need power sets to exist in your category. So what does Cartesian closeness mean here? What is exponentiation? What is exponentiation in a general category? Remember, we introduced the notions of product and sum by being motivated by arithmetic. We said that these are the things that allow us to carry over arithmetic from the traditional mathematical environment of numbers, of finite numbers, which are represented by us by finite sets, to general categories. But exponentiation is a very important part of arithmetic, right? Maybe it doesn't come up immediately, but it comes up after making two steps in arithmetic. So what is exponentiation? And we already know what it is, said theoretically. We can represent exponentiation as the set of functions. If I have two sets, x and y, So in the category of sets, for x and y, the set x y to the power x is the set of all functions from x to y. Now, in a general category, you can still consider two objects and consider all morphisms between them. But this will be a set. It will not be an object in the category anymore. So this is not good enough. We somehow want to be able to represent this, whatever the structure of all morphisms, to be represented as an object itself in the category. Let me give you an example. If we take, for instance, not the category of sets, but if we take the category of vector spaces, or even simpler, the category of abelian groups. If we take all homomorphisms between abelian groups, let's actually take vector spaces. It's more standard. If we take all linear maps between vector spaces, the set of linear maps from one space to another itself forms a vector space, right? So it's not just a set, it's an object in the category of vector spaces as well. And that's what we're trying to define here. And it turns out we can define it using a universal property, which will be a special case of the type of universal properties that I initially wanted to talk about in this lecture. So, what is the universal property that defines exponentiation? Well, it's the following one. This is an object defined by the following universal property. Remember, the spirit of universal properties is that I need to be able to write down what are the basic things I want from my construction, then form the category of all such basic things, and in that category, either the initial or the terminal object will be the thing I'm trying to define. So what is the most basic thing I want from the set of functions? So I'm now trying to take an abstract set, and when can I say that an abstract set is a set of functions? How would you answer that question? What is the most basic thing we want from functions, basically? I think it has become x to the power y. Initially, I started with y power x. So let me switch to that. What do we want from a function? Would you like to answer that?
Well-definedness, that's what's coming to my mind.
Sure. But before even talking about well-definedness, I need to be able to do something, right? How do we use functions? What's the purpose of functions? What is the most basic thing we do with functions?
Yeah, there are mappings from one structure to another, one element to another element.
There are mappings, and computationally, what does that mean? When we write down expressions with functions, what do we do with them?
Or computationally, no, I thought you meant in terms of a diagram.
Yeah, I'm kind of trying to get rid of the set theoretic diagram for functions because we're now in an abstract category, and so functions there might be different things. So I'm rather trying to reveal kind of the algebra behind. That's what you need to do. You need to hide the geometry inside your objects and reveal the algebra of compositions, basically, in category theory.
So Alexandra says that they have to respect structure. I don't know.
Well, that will come for free. That will come from free from universal property. So in very, how would a bad teacher, let me put it this way, how would a bad teacher define what a function is? A bad teacher knows very little, right? So if I'm asking the question, what is the minimal information about functions, then it's equivalent to asking how a bad teacher would define a function.
Yeah, I don't know. Yeah, I think just a mapping from one. Yeah, taking something, transforming
The term
something.
mapping, a bad teacher never uses the term mapping. A bad teacher doesn't know what a mapping is.
Changes an input, takes an
There we
input
go.
and then we get
There
an
we go,
output.
Kotisa, you're on the spot there. So what a function does is it transforms an input into an output, right?
Yeah.
It evaluates two variables, right?
Okay.
So if I have a function f and I have a variable x, let me write it on the other side. If I have a function f and I have a variable x, what a function does is out of these two things, it produces the value f of x, right? Now this itself is a mapping from this Cartesian product to y, isn't it?
Yeah.
It's a special mapping. It's called evaluation, right?
Okay.
It's called evaluation mapping. Let me forget the subscript x because let's agree that x is fixed here. So that's what it is. And now we're going to build a category of such things and then take terminal object there. So the primary function of a function is to be able to compute its values. So we've got this mapping. Consider the following category. Inspired by this, consider the following category. Objects are morphisms, sorry, pairs rather. They're pairs of the form A and let's say V, where V is a morphism from A cross X to Y. So both X and Y are fixed here. A morphism from AV to, let me rather call it BW. Morphism from BW to AV is a morphism from B to A, let's call it F, such that the following diagram commutes. So I could take B here, I'll have B cross X, I'll have A cross X, and I'll have y. And here I have my v, and here I have w. And I can form here, and now for now, let's just think of it in the category of sets, because for a general category, we might not have defined this yet. I can form here a morphism called f cross identity of x. So what is that morphism? So let me explain that. If I draw a product diagram, b cross x, of course, element-wise, what it does, it evaluates a pair by evaluating the first component by f, and then the second component just stays the same. And the way we can get this categorically is I draw my product, two product diagrams. So here is f, and here is the identity morphism. And then this gives me a cone. By composing these two, it gives me a cone over my discrete diagram consisting of a and x. And by the universal property of product, then there will be a unique thing here, such that this composite with pi1 gives me this yellow arrow, composite with the pi2 gives me the other yellow arrow. And that thing is called f cross identity of x. So it's the one that comes from vertical maps f and another vertical map. It could have been a g, but in this case, it's identity of x. So so we're considering, so you see, we've got this evaluation map here, right? But now we are considering all possible types of evaluation maps. So imagine I have an abstract set A, which maybe is some kind of abstract kind of functions, and if they behave like functions, then they should be able to act on elements of x to get elements of y, right? And so that's what we're basically saying here, that we have an action of this set on x, as a result of which we're generating elements of y. So every pair ax gets mapped to this v. You can think of it as value of ax. In other words, we can think of this as value of a at x. The exponent, not the exponent, but the exponential y to the power x is defined as it will be unique up to isomorphism, as an object in the terminal object in this category that we just described. So the terminal object will denote like this. The object part will denote y to the power x, and this evaluation map will denote by EV subscript y.
Sorry, I quite don't understand what we have written here. The exponential is defined as an object in the terminal object.
Yeah. Maybe I should say here as the first component.
So, okay.
Because the objects of this category consist of object and morphism. So
Yeah, now it's clear, yeah.
Yeah.
That was my confusion, yeah.
Is defined as the first component in the terminal object in this category. So let's kind of we don't have too much time maybe to step deeply into proving this, but let's confirm some part of it. So let's confirm that when I do take my exponential and the evaluation, let's confirm that for any other evaluation, there will be the unique morphism connecting to this one. So if I have another evaluation, let me call this ax, some v. Let's confirm And remember, morphisms between evaluations are morphisms between the first components. So there must be a unique morphism here, unique morphism F, let's say. Maybe F is not a good name because we use it for functions. Unique morphism U from A to Y to the power X, such that this diagram commutes. Because the commutative diagrams are the morphisms, are the properties that define morphisms, right? So it must be unique U such that this commutes. In other words, so here we'll have U cross identity of X. Right? So we want to show that this diagram commutes, and that there is such U. So let's at least find it, and then maybe we will not prove that it's unique. So this is some abstract evaluation, and I want to now reduce it to the usual one. So how do you think I will define my U? So I'm given, what am I given here? I'm given sets X and Y. I'm given this very specific thing. It's the evaluation map. We already know what it does. It maps pair Fx. It maps it to the value of F at X. That's given 2. And then also we're given that we have an arbitrary other evaluation. We're calling it evaluation, but it's a very general thing. It's just a map V from A cross X to Y. So it's a function of 2 variables. And now I want to, out of this data, I want out of this data, right? Out of this data, I want to produce a map from there, which will make the diagram commutative. Maybe we should write down, like before, we should write down what would make this commutative. So if I take an element AX, right, and I apply this top function, I will get what? I will get U of A X, right? When I apply evaluation, I will get U of A, which is now a function of X, because it lands here, right? U of A of X, right? That's the value of this function at X. That's what I will get. On the other hand, if I apply this left side function, I will get V of AX. So essentially, by saying that we want this to commute, we're saying that we want VAX to be equal to that, right? Now, the question is, and this we want for every A and X. In fact, maybe we actually can prove uniqueness as well because it's rather simple. So now the question is, will I be able to find a U and a unique one for each V such that this holds? So first of all, will U be unique? And then we'll see why it exists. So why is U unique? Well, what is a U? U is a function, right? So a function is defined by its value. So to prove that U is unique, I need to prove that U of A, for every A, U of A is unique, right? That it's U of A is some fixed function. Well, U of A being a function, its uniqueness means that its values are uniquely determined, right? So I need U of A of X to be something that's exactly 1. And that is, by this equality, it must be V of AX. So each UA must be the function VA dash. Then U must be which function? The function that maps every A to VA dash. And so then if it exists, it must be this one. But now we can use this one to prove existence because this one will work. It will be well defined, since B is a well-defined function. Questions?
No, no question.
Is it clear?
Yeah.
Okay, great. Alexander, is it clear for you too?
Yeah, I'm fine.
Okay, good. Okay, great. So we then have been able to show that our usual exponentiation has this universal property, and this is how we can define the universal property in general. Let me very briefly give you a hint as to what I wanted to do in the lecture initially. So this process of assigning to an object A, the object A cross X itself is a process between two categories. So if I take the category of sets twice, I can think of this functor. So this is a notion of morphism between categories that maps an object A. It maps to A cross X. So this is the functor dash cross X. Now, what we've been able to do is to say that for a given object Y, there is sort of way of going back by mapping Y back to Y to the power X. It is not quite going back because when I do that, when I take Y to the power X, and when I apply this function to it, so when I take its X times X, it will not be equal to Y, but there will be a morphism between them, the evaluation, which will have this universal property we stated. So the universal property we stated can be stated actually for a general functor as well. If I have any functor between two categories, we can state a universal property which says that there is approximately a way to reverse this functor. And that's the universal property I wanted us to discuss, but probably we'll do it next lecture. So this is a special case of this. Now, going back to the definition of a topos, because I still wanted to tell you what is the purpose of a topos. So now we know what it means for exponentiation to exist in a category. By the way, limits of finite diagrams, they reduce to two kinds of limits. They reduce to limits that are products, so limits of discrete diagrams, and the things called equalizers. An equalizer of two morphisms is a limit over this diagram. So it's, maybe I shouldn't have used yellow color for that. So if I have a diagram of morphisms, F and G, a limit over it is called equalizer. It's given by two morphisms, something here, which of course will be uniquely defining the other one as well, because the other one will have to equal to the composites. And the fact that this is a cone will force EF equaling GE, sorry. So it will be a morphism E such that EF equals GE. And if I have another such cone, which again will force the other one to be uniquely determined by the left one, where here I have E prime. So if I have another E prime that makes F and G equal, then I must have unique morphism going here. And in the category of sets, this will turn out to be exactly the set of all those x's for which F of X equals G of X. So I mean, we don't have time now to enter in detail here. I just want to say that equalizers are very, very simple kinds of limits. And there is a general theorem that any kind of limit, well, any kind of finite limit, decomposes as a combination of finite products and equalizers. So the fact that we're requiring limits of all finite diagrams exist is actually not a very strong requirement. In fact, let me not say most, but in large part of category theory, you always want to work in categories that have limits of finite diagrams. So it's a very standard thing to require. What is strong, though, are these two things, especially together. Already, combining them together already allows us to define power sets, right? Because I have my 2 and I have my exponentiation. Well, now I can take 2 to the power x. That will be describing a power set object. And there is a separate universal property for the power set object, which I could state, and then I could merge these two. So why are these axioms interesting? And why is this called an elementary topos? And what is a topos? So here is a brief history in 2 minutes. Alexander Grothendieck, when revolutionizing algebraic geometry with category theory, he introduced this idea of the category of sheaves over a given category equipped with something called the Grothendieck topology. So these are basically functors. Sheaves are functors from a given category to the category of sets. And these categories, functor categories into sets, so it's kind of exponentiating at a higher level. So we have the category C, and we consider all category of functors from C to set. Morphisms, there are things called natural transformations. Sheaves are special objects in here. These categories turn out to have very useful properties, and that was the key of why they were significant in algebraic geometry. And two category theories, one of them being Bill Lovier, noticed that we can almost axiomatize these nice properties of those categories of sheaves. So Grothendieck was calling them toposes. A topos is a subcategory of such a category, which is given by a certain structure on C called the Grothendieck topology. And so elementary toposis is an attempt to axiomatize these categories of sheaves or general toposes. And the axioms are what you see here. And the powerful consequence of these axioms is that all of intuitionistic mathematics you can do inside any elementary topos. And why do I say intuitionistic? Because, well, so to really get all of mathematics in my topos, I need, in addition to being elementary, I need elementary topos, I need for it to have a natural number object. This will ensure that there are infinite things. And the definition of natural number object we already know. That's the universal property we gave earlier about universal counting system. And then what I also need is that the sub-objects of my sub-object classifier, arbitrary things going into my sub-object classifier, they form a Boolean algebra. So that would be then called a Boolean topos. So if these sub-objects form a Boolean algebra, where inclusion of sub-objects is defined just as factorization of morphisms, then I can, and I have the natural number object, then I can do really all of mathematics inside my category. And it becomes particularly important because then these categories of sheaves, which are very geometric things, will be able to model mathematics inside them. And this way, geometry, very advanced geometry, became connected with logic, and it was one of the biggest breakthroughs of early days of category theory. There was no such connection between logic and geometry before. It was kind of for the first time that logic got connected to geometry through this notion of elementary topos. So the notion of elementary topos is the notion you want to work with if you want to do sophisticated logic using category theory. At the same time, topos is the notion you want to work with if you want to do sophisticated algebraic geometry using category theory. So that concludes today's lecture.
Thank you, Zurab. Very riveting, and yeah, yeah, and I don't know. Yeah, a lot to think about towards the end.
Mm-hmm. Thank you.
Indeed, cool. That was indeed interesting.
Mm-hmm.
I totally liked it. And especially, I have never seen this definition of monomorphism.
Of what, sorry?
Of monomorphism.
Oh, that you have seen from last year, but you might have forgotten.
Yeah. Yeah. Oh, it's a fun story then.
Yeah. But it's okay. You're still in your first year, right? You're in your first year. So when we talk, when you'll be in the third year, Maybe you will tell me that you've never seen the definition of a self-object classifier. But
So
maybe it was more meaningful now than it was before because of the context that we looked at.
Yeah, probably.
I just wanted to ask, so are push-outs and epimorphisms kind of duals to the things we were talking today, or they're just closely related?
Push-outs are dual to pullbacks, yes, and epimorphisms are dual to monomorphisms. That's right, yes. And that's another remarkable story, that surjective maps turn out to be dual to injective ones, which is something you can't really see with sets, because surjection is a quotient and injection is a subset, and so they don't seem to be very dual to each other, apart from the fact that when you draw it as arrows, they go opposite.
Okay.
So what I have seen here, when we define this exponent object, we mentioned that it is a terminal object. So the intuition behind taking a terminal object, is it that we want to catch all possible objects in the sense that it has to contain everything that satisfies certain conditions? Is it so?
Yes. Yeah, sorry.
Yes, that was my question actually.
Yes, you're right. So you see, each individual AVs, they kind of capture some functions, right? Because if you fix A, you're gonna get a function from X to Y, right? So every small A gives you a function. But now we want all of functions. So somehow it's natural that we want terminal object, because then it will contain all of them. So there is this subtlety that I also mentioned last time, right? Because although, I mean, it's not the biggest, right? Because you can have like a very large A that duplicates functions, but the universal property kind of allows you to disregard the duplication. So you really take all different possible functions, put them together, and then you get your exponential.
So that uniqueness means that we ignore these duplicates and think about uniqueness as that, yeah?
Yeah, if we allowed duplicates, we would lose uniqueness. That's right, yeah.
Yeah, fine.
The existence is the one that allows us to say that it kind of must include all functions, but then the uniqueness part of the universal property ensures that duplications are disregarded.
Fine. So that we told earlier that for finite limits to exist, it's totally enough for co-equalizers and I think products to exist.
Equalizers and products, that's right, yeah.
Yeah. Does it mean there exist every finite limiting groups, for example, and
Yes.
topology as well?
Yes.
So
Both limits and colimits. In fact, even infinite ones exist, but of small size. So your diagram must be a set. It cannot be a class. It turns out that if you force existence of limits over diagrams of large size, so diagrams that are not necessarily sets, then you will be forcing your category to be a preorder. That's another way of thinking of preorder, to think of them as kind of super complete categories. Remember, preorder is the one where we just have binary relation describing the structure.
So in another case, in infinite case, we usually take small categories, right? Or small diagrams or something.
We take small diagrams, yes, but we don't want the categories always to be small. The category of groups is not a small category. So it's a large category, but it has all small limits and all small colimits. It cannot have all large limits and colimits, then it would have been a preorder if it had.
So why is it not a preorder?
Why is the category of groups not a preorder?
Yeah.
A preorder is a category where between any two objects in a given direction, you always have at most one morphism.
Okay.
It really forces your morphisms to be equal, the parallel ones.
Understandable. Thanks.
So all standard categories have these limits. Yes, Kotisa?
So the notions of first order, second order, they're the same as in mathematical logic, variables and what is quantifiers existence.
They're
So
not the
you-
same notion. It's similar in some sense, but not the same at all. In logic, when we talk about first order logic and second order logic, this is not about iteration of quantifiers. In first order logic, you can have sequences of quantifiers of arbitrary length, right? But in first order logic, you cannot quantify over formulas. So you've got your variables, and then you've got your formulas that apply to the variables. And you can quantify
Yeah.
over variables, but you can't quantify over formulas.
Yeah.
So it's a different kind of, but in that sense, it's analogous. So here we are, whatever we can do at the first step in the first order universal property, here we can now also do the second step of that.
Okay. Okay.
So in first order logic, I can form these expressions as long as whatever I'm quantifying, each of these are variables.
Yeah.
So both of these will be first order formulas. So they do belong, higher order universal properties are still first order properties from the sense of mathematical logic.
Okay. Okay.
Thanks a lot, and to the next time then.
Thank you. Yeah. So last lecture next Saturday. Hope to see you then. Thank you.
Goodbye.
Bye.
All right. Goodbye.